my talk today has to do with the use of machine learning techniques, or particularly these important neural networks, for the solution of Quasinormal modes in modified relativity theories. Okay, so before I start, well, I just wanted to give a bit of context for this, the use of these neural networks or these kind of techniques for solutions in mathematics or PDEs in this case. Well, as you obviously know, there's a really high interest in developing this kind of machine learning techniques for many reasons, most of them in industry, like, well, all sorts of models, right? And all of these models have to do more or less with trying to fit some very complicated function with some interpolate, right? Like the most common example are neural networks. And so we have built, and we continue to build, better and better codes and implementations, and also machinery like GPUs and all these things that are specifically optimized to do fits of complicated functions, right? So it's of course interesting to have a look at the possibilities of these things for mathematical problems, like the solution of differential equations. And this is what we are doing here. Of course, there are already many algorithms like traditional numerical methods that one can use to solve differential equations. So I think for now, the interest of this machinery is for kind of unusual or particularly difficult problems where there's no obvious solution in terms of traditional methods. And in this particular case of the Quasinormal modes, this is arguably a difficult problem. It's not so easy to get Quasinormal modes using traditional techniques. If you have an analytical background, such as the Kerr black hole, there are techniques to do this. The most successful one is probably the Lever's continued fraction method, but of course that needs the differential equation to have be purely analytical, so we cannot have numerical coefficients. And so it's interesting to try these techniques when you have, for instance, modified gravity theories where the background is actually numerical, so you cannot do that. You could also use spectral methods. I will comment on that later. But even with spectral methods, this is not a problem that's immediately solved. So it has some problems too. So that's why I wanted to apply these techniques to this particular problem. So let me first start by introducing briefly what the neural network is and what we are doing when we say we are training these models and what we mean by deep learning and all this stuff. Okay, so this introduction. So as I said, the idea behind machine learning is to fit things, right? And I want to start with this quote by General Raimon, where he was arguing that in physics problems you shouldn't actually use too many parameters, because if you use too many parameters, you can fit whatever. I mean, independently of which particular model you chose. If you have 4 parameters, you can already fit an elephant. You have 5, you can wiggle the trunk. So in principle, physical models should have just a few parameters. In machine learning, we do just the opposite. Okay, so just let's introduce many parameters. We don't care that much about the model architecture as long as it can reproduce the data that we're taking. So for instance, this typical disease is already old, but it has this kind of 10 to the 11 parameters, right? So here we just throw a ridiculous amount of parameters and try to fit whatever function we need as accurately as possible. And well, for multivariate functions, you have many ways of trying to approximate them or interpolate them, right? So these are the more or less standard traditional ways of doing that with a moderate number of parameters. But here in neural networks, we kind of take a different approach, and we start by defining this thing, which is just a linear transformation, right? So you have some input. This could be a large vector of numbers, and you do the whole general transformation. So you multiply the matrix. This thing in the machine learning lingua, we call it the weights matrix, and then this constant term we call it a bias term. So the weights and the biases. So with this transformation, you can go from one vector to the other. Okay, good. Okay, so then the thing is that not all functions are linear, so it's nice to have something nonlinear. So you add this function, that's called the activation function, and it's kind of inspired on real like biological neurons, where you can have that the neuron is not active or active. So neurons get some input information, and at some point they spike or they get activated. So we started using these things that typically a function goes from 0 to 1 in a more or less smooth way. So if this thing becomes large enough, then the output is close to 1. If it's not, then the output is close to 0. And this was used mostly for classification. You have many points and you want to define some boundary between the positive points and negative points. You can do some higher dimensional transformation in this space, and you pass it through this function. This function will like divide some part of the domain. Will kind of divide the domain in active and inactive points. For this activation function, you can use whatever. The traditional one is the sigmoid thing, from 0 to 1. You may know this in physics as the permitted active distribution. Then people started using other things like this one that goes from -1 to 1. This is actually quite convenient. It's very simple, but it's quite convenient because this gradient is always large. Just the rectified linear unit, so it's just the identity function here and you're there. Then it was shown that actually having a 0 gradient here is not that good. So people introduced the rectified linear unit, do the same, but just add a small here. And you can keep inventing these things, okay? So then this part here was called the perceptron, because it can be used for very simple classification problems, but people started, stacking these things together, right? So you start with the first layer, you pass it through this thing, and then you use this thing, you plug it back to the second layer with different weights, different biases. You repeat this explanation function, and you do this many times. And the typical way of representing this kind of operations is like this. Okay, so here you have the input layer, and so this number we call verbs. So you start with some numbers here, and this goes to the weight matrices, and it becomes another list of numbers, and you can repeat these things. And so the numbers, these vectors, play the role of neurons, and the weights play the role of synapses, connection between neurons and neurons from one layer to the next layer. So you can go forward from one layer to the next until you get the output layer. And so this interpolates. It has been proven that this can interpolate an arbitrarily complicated. But then, of course, if you want to interpolate, how do you decide which coefficients to use, like which weights and which biases to use? So what you do here is like we don't have a simple algorithm like in the other interpolants, but we actually have to do it iteratively, right? So we define this thing that we call loss function, which is a measure of the distance between what we are getting from the network and what we want to get. Yeah, so if this thing is large, it means that the network is not doing well, it's not interpolating very well. If it becomes small, it means that we are getting close to what we want. Right? So the way to define the weights and the biases is to take derivative of this. So of course this loss function will be a function of all the parameters, like a high-dimensional function, and we want to go downhill to find the minimum. And the algorithm, the standard, like most basic algorithm that we can take is the gradient descent, right? So you take the weights and you update them by adding a small fraction of the gradient, or subtracting a small fraction of the gradient. This epsilon parameter is a small parameter. That's called the learning rate. Okay, so if you do a very small thing here, then it will take you very long to converge. But if you use a very large number, then you could oscillate around it. And then people started improving this thing, right? So now by far the most used algorithm is this ADAM, it is adaptive momentum, which is pretty much this thing, same thing, but you add some inertia to it, right? So you add some momentum to the thing, so you cannot well, you don't oscillate too much. Some people get steered to the main one. And believe it or not, this is the most cited paper, guys, where the paper where they actually introduced this method. So it's a measure of how much interest is in developing this kind of things. Okay, and then of course here you need the gradients. And to compute these gradients, you use the chain rule, but you use the chain rule in a smart way, because just to compute things in an efficient way, you start going from the end, like you know how the loss depends on the last layer, and then you use the chain rule, for instance, to go from the last layer to the last weights. Okay, like this. And then if you need the gradient with respect to the second to last layer of weights, you use the thing, right? So again, the chain rule. But this part here, you can see that you can use it again. So this thing here, you're using it again, and then so whole thing, you can sort of recycle these terms here to compute the gradients in previous layers, right? So if you do this and you keep like storing all the gradients along the way, you apply the chain rule in an efficient way. So you don't have to recompute all the terms every time. And these things go backwards, right? So when you start at the end of the network, and you keep applying these chain terms backwards until you get to the first layer. And that's why it is called back propagation, right? Because you're computing things from the end to the start. And then when you evaluate the network, you call it a forward evaluation or forward propagation, because you go from the input to the output. So you keep doing this forwards and backwards computations all the time. Okay, so now that we are here, let me just try to do this correspondence between what we say in machine learning and what we actually mean, right? So when we say this fully connected neural network, there are other types of networks, but there's the simplest one, and we just mean that, just successive application of multi-layer perceptrons like this. So just linear transformations inside nonlinear functions. When we say deep learning, we mean that we have many layers. So basically more than 2 layers. So if we do this more than 2 times, we call it a deep neural network.
That nonlinear function you're applying a component lines.
The nonlinear function, yes. And then we call training or learning or whatever, just finding a minimum in the loss function. Okay, so this means doing a fit. I mean, it's a very complicated fit, but it's a fit. And backpropagation is an efficient way of applying the chain rule. Okay, of course, this is the simplest neural network. Now we are using, for other applications, we use models that are more adapted to the particular kind of problem that we want to fit. So, for instance, if we want to process images, use convolution. So things that where the network doesn't actually mix linear combinations of all the numbers that it gets, but it instead just decides on parameters for a convolutional operation. And this is good because these models become sort of shift invariant. So you apply some model in one part of an image, you behave the same way as if you apply it in another part. So this famous net, AlexNet, whatever, all of these were convolutional models. You have things that come in a sequence, like one after the other, and have some causal dependence, like human language or some time series or whatever, or stock values, whatever. Then you need something that's recurrent. So that takes the output of one element and then plots it back to see the next element. We keep doing that to adapt to this sequential structure. Then from here, people started applying this some attention mechanisms that are described here, but some extra machinery. And at the end, this attention mechanism gave, became this transformer models, which are just the attention part without the recurrent network. And these transformer models are the T's, of these BERTs, GPTs, whatever models that are, of course, being used for language, as you obviously know, right? Okay, so this is like the short introduction to the kind of tools I'm going to be using. So let me move next then to the physics. Okay, so the kind of physics we are solving here are Quasinormal modes in this kind of theory. So these theories are just the Einstein field protection plus some scalar field, and then we introduce some coupling between the scalar field or some function of the scalar field and the Gauss-Bonnet invariant, which is part two. Okay, and this is some common model for modified relativity. And of course, we are free to choose for the coupling and also the coupling constant and the coupling function. Okay, and this function has to obey certain constraints if one the theory to be well behaved. But in this case, we will consider this thing, which is a quadratic coupling, and then we call it quartic coupling. Okay. These systems were already studied in this paper, in particular the first one. And you can get black hole solutions. We will be using slightly symmetric black hole solutions of these models. Okay, so from that action, you can get a perturbation equation, which is kind of analogous to the direct Wheeler equation for traction. But now you have some extra source terms, if you want, coefficients here that depend on the numerical solution. So this equation is no longer something that you can solve with kind of paper, more or less, but you actually have to consider these functions that don't have any particular shape or just a numerical value, right?
So yes. The background solution is not perfect. It's some other.
No, the background solution is some numerical thing. So it has a scalar profile. Okay, so how can we do that? Well, first we do some tricks. Of course, we compactify everything. We make this frequency dimensionless, blah blah blah, and we have to impose this kind of boundary condition. So this is equivalent to having a solution that's outgoing at infinity and ingoing at the horizon. Okay. So once we apply all of this, we get that this g function here is a perfectly finite and smooth function between 0 and 1. So now it is at 0, the horizon is at 1. That has to obey this differential equation. This looks very horrible, but it's just linear combination of d derivatives of the second order and powers again of the second order of this omega. And then this prefactor, I mean, this you could factor out, but it turns out that you have to give this for methods to behave properly, both spectrum and the neural network. So I left it there. Okay, so the only thing that you have to have here is this a and m coefficients, which are actually functions of x between 0 and 1. Okay, and these have just a numerical equation.
The end with the method.
Sorry?
The end there.
Is that?
Yeah.
No, this is just an index for the power of the, so for the order of the, yeah.
One quick question. So you're compactifying in the radial direction. Does that mean that the background numerical solution is also obtained in a compactify?
Actually not. The ones we used were just in Schwarzschild-like coordinates, but we know them up to a kind of large rate. So,
And maybe you can fit to some asymptotic expansion that's analytical.
well, yeah, they have an Schwarzschild-like. Okay, so, well, as I described, there are many methods to solve these eigenvalue equations for particular Quasinormal modes, which is a particularly hard eigenvalue problem. Some people just do the evolution of the equation. That's a way, because I mean, you can extract the first mode quite easily, but it's computationally costly. Then there's this, which is, I would argue, the best way if you have an analytic equation. It's the only one I know of that can extract like a really large number of Quasinormal modes with good precision. But this requires expanding things as a series expansion, so it's not easily applicable to numerical methods. Then people do all sorts of things with methods, all of these quasi-analytical kind of approaches that have inspiration in quantum mechanics, blah, blah, blah. There are spectral methods which also work in this case, but sometimes they are a little bit delicate and you get a lot of skews, like on physical modes that you have to filter out. You cannot provide if the numerical error somehow drives you away from the good solution, you cannot provide an initial guess to the method, so the method will decide kind of where to go. And then static methods like the Large expansion is the thing as well. Okay, so here what we propose and what we did is to, okay, what if you just take the function? Okay, so you just take the equation. We know that all of this we want it to equal 0. So what about we just interpolate this G with a neural net, impose the boundary condition? Well, not the boundary condition. This is actually a normalization condition to the linear equation. So we want to fix the scale, and we just fit this G for it to satisfy the equation. Okay, so this normalization condition, we impose it in this very strange way, but this we call a hard enforcement of boundary conditions, which means that we take whatever comes out of the neural network, we multiply by this, that clearly goes to 0 when x equals 1, and then we add 1. So whatever the network decides to do, the solution will have this normalization. So it will always be 1 at x equals 1, not the price. Okay, so this is kind of the architecture of the whole thing. It's a black box, not a box of neural network, but you don't really have to worry too much about what this thing is doing. Just trying to interpolate or to produce an approximation for g of x, and also the frequency. So there's an extra parameter that we have to train, that we have to tune. Okay, so first we take the background solution, we do all the numerical derivatives or whatever, and we get these coefficients here. And these are well, some functions, some numerical functions that have some values on our computational points, but we, even if these equations are quite complicated, okay, we have to compute them once, and that's it, right? Okay, so we get a file for these things. And then what we do is, okay, we plug this into the, what we call the equation loss, which is just the right-hand side of this. So a metric that we actually take the two metrics, so the mean and squares of the fields here. So we plug it here, we see how well the equation is satisfied. And then we use the Adam optimizer to tune the function and the eigenvalues for it to approximate better the differential equation, right? So we keep improving, we keep doing this loop over and over, and we keep improving the approximation for the equation to be better satisfied.
Where is the little omega that it was?
The little no, this is So the big omega is just a dimensionless version of the omega. So it's just that.
So in your previous language, the loss function is like the right hand side of this.
Yeah, exactly. So in practice, we just choose a number of points, of computational points in the domain. It doesn't have to be like a particular grid. We can choose random points or whatever. In this case, it's a equally spaced grid, but it doesn't have to be. And then you evaluate this equation, the right hand side of each of the points, and then just take the mean and the squares or whatever. Okay, so now I'm going to show you a video which is not exactly real-time computation, but pretty much. So it's more or less this how long it takes to compute for the particular case of care, and you can see how it goes. Right? So for this here, actually, this is not spherical symmetry. This is the only case that I'm going to show that has x, so radial dependence, and angular dependence. Using the cosine of theta. Here you can see the loss decreasing as as we keep it rating. Here again, the machine learning community we call epoch and iteration. Okay. So we're doing iterations, and you can see that the log is decreasing. Well, sometimes exponentially, sometimes not so much. At the end, it stabilizes at some low value. And here you have the null value for this mode at particular speed, and you can see how the spin mode is converting to the right value. Okay. Both real and imaginary parts. The other A thing is the separation constant that just happens to appear when you have a non-spherical symmetric solution. Okay, we actually published this in a previous paper. It was the first attempt at doing these kind of problems. And you can see that these functions that we are feeding are actually smooth. They are obeying the boundary conditions that I said, so x of 1 equals 1. So f of x equals 1. And well, this is the basic idea. Okay. And the nice thing is that this is an iterative process, so you can provide, if this function is a bit complicated or whatever, we can provide with an initial guess, both for the function and for omega. Okay, so here we move to the actual modified gravity problem. In this case, this is for the quadratic potential, for which we already had some modes computed with other methods. Here you can see the comparison. So the green dots are the modes that we had before, and the orange ones are the new ones, so the pin, the neural network modes. You can see they coincide pretty well. The blue ones are the for GR, which is just one of the other percentage. And here, the funny thing is that, as you can see, the pin didn't get as far along the branch as the previous methods. And this has to do with the fact that these models encounter a lot of hyperbolicity of equations at some point. So if you keep taking, there's some coupling here. So if you keep changing the mass, so you are moving along this branch, at some point the equations are no longer hyperbolic. So the theory kind of breaks down at this point in life. And it just so happens that the pin didn't work after some. I mean, if you get too close to the hyperbolicity loss, then you stop getting the good modes. Okay, so here. There are modes. I think it's some kind of WKT kind of approximation, but this is a different paper. I mean, I don't know the exact detail.
Another question. So the machine learned model.
Yeah.
Does it converge?
Yeah, that's the question I never want to encounter. There is no clear answer to that. I mean, people know that have been playing with it, and there's some sort of convergence, but it's a convergence that you cannot prove first, because the method is just an arbitrary function, or at least for I mean, maybe for a very simple network you could prove it, but not in general. And it's not so clear. That's why, for now, these methods are kind of a useful tool or something that years I think somebody has to study, but it's not something as robust as spectral network or finite difference. On the other hand, this I'm pretty sure you cannot do that with a finite difference. Okay, so yeah, this is just a table. I mean, don't put the numbers, but I just want to show that the error percentage is reasonably low. I mean, it might not look that.
Well, at this point, in the end, you have a function, so that's the advantage, right? You have
Well,
a
yes,
function, right? So
you have an
test the
interpolating function already. Yeah,
Test the function.
yeah. Well, this is what we're doing pretty much. Yeah.
So
The only thing is that you don't have this idea that you can make the error go as low as you want by increasing the resolution. So you don't have a control of how small the error becomes. Got it. So yeah, exactly. In that, so regarding that question, actually, so here we have the loss, which is exactly that. So it's a measure of how well the differential equation is being satisfied. And you can see here that the error loss, our particular units, is pretty small. But then here that we actually know the error because we have a solution from the literature, we can compare, okay, what happens when the error gets large, right? So here when we approach the loss of hyperbolicity, we see that, well, first the error, the percental error with respect to the original results becomes a lot larger from 0.09 or whatever, 4, 52, whatever percent, huge error. And this translates as the equation being fully satisfied. Okay, so this error is becoming large. And for this, we do need previous solutions, but for that we don't. Okay, so that we can always apparently measure that thing. So the conjecture here is that, okay, when we see that the equation is not very well satisfied, then we cannot trust the control mode values. Right? So here's more or less what we did. So here I'm plotting the error using the previous result in the literature. Here I'm plotting the percentual error, and here I plot the final loss that I obtained in the training. So you can see that when the error becomes large, in a more or less something that resembles a power law, you get that the loss goes larger. So you can set a threshold and say, okay, I'm not going to trust any solution that has an error larger than whatever. In our case, we chose 0.1 here. Okay, so, and you can see that actually as the blue points are for GR. So here the network modes are always providing very small losses, so we can trust them, and we see that the values are the correct ones. But instead, with this quadratic theory, we see that as we approach the hyperbolicity loss, the errors become super big, like the values of the loss. And this actually, well, it correlates in a good way to the precision we know we are getting. Right? So we can plot it here and say, okay, from here on, don't trust it. Okay, so there is still some way to decide if we can trust the results. So then once we had this, we said, okay, let's move to a case that hasn't been studied before, so for which we don't have solutions from other methods. So we moved to this quartic model, and this is interesting because the branch doesn't connect the GR directly. So, well, here it is. We have like different beta parameters like this. You have to choose the right things to plot for it to be really different from here. But well, we got these curves, and in this case, we know where to plot them because so we could keep drawing this point here, but since the loss became too large, okay, here is where the method ends. And okay, so this were the first calculation for these modes, and actually later on we tried the spectral methods and they can so be okay. And again, as I was describing, here you have the loss as a function of this mass parameter, and you can see that again, PR is very well in all the cases, but all the others start rising when you approach the loss of hyperbolicity. And so the network is actually telling you that there is some problem with the theory. So we are not completely blind. Okay. So now, are there any questions before I can do?
So physically, this quartic model, I guess, the differences with respect to GR should be more confined to the vicinity of the black hole.
I think they are more compact, but I will have to confirm exactly.
Right, question.
Yeah.
So, the fact that your loss is increasing when your M over lambda is low, you said that it means that there is something wrong with the theory, but it also means that the algorithm of the dimensional model is not able to really find the solution.
Yeah, well, I mean,
How do you disagree?
yeah. So, I mean, the only thing that the loss is telling us is that the algorithm is not succeeding in finding a solution. That's the only thing I know, for sure. But then we can interpret this as, okay, the algorithm is failing because it's getting closer to solutions that are pathological. Okay, so it's just, I mean, it could be that it's failing for another reason, but since we know that actually these vertical lines are known to be the hyperbolicity loss points, then we say, okay, it has to do with that. Actually, the more traditional methods also have this kind of problems. As you approach that, you start getting answers. Okay, so let me just summarize a little bit and well, what I meant by this. Well, the first one is the thing that you can use spins as a really quick and easy way of finding approximations to solutions of OEs, PEs, whatever, with one or many eigenvalues or parameters that we want to take. Okay, this is something that's really nice because the code for this is like half a page, right? So you get an equation, you don't know what to do with it. So before you try a very sophisticated code, you just try that and see how it the implementation is super simple. All of this is already implemented in PyTorch, TensorFlow, standard machine learning codes. Even the derivatives are performed automatically, and it's a great advantage of these methods is that you can do it in half an hour. Okay. Then the computation time is obviously a lot larger because you're doing gradient descent, so you have to iterate many times and have large numbers of parameters and everything. But these things are trivially moved to GPUs or all this specific hardware that's kind of designed to do that. Okay, so people are very interested in this machinery for other reasons, train language models or whatever, but we can use the same machinery to do that. The performance is kind of competitive. I mean, it's slower, but the precision, believe it or not, is not much better with spectral methods for the backgrounds. And well, it allows you to work with numerical backgrounds, and especially it allows you to provide with an initial guess. And this is important because you can go from one mode to the next along the branch, and you can give as a starting point the previous one, right? So this makes the method be kind of self-consistent and robust, so it doesn't move too far from the right solution. This is something you can not do with spectral methods, for instance. I tried it, and some of the modes in some particular points just didn't work. Just that numerical solution was particularly bad or whatever, and then the method doesn't know what to do. In this case, you can tell it, okay, it has to be around here, so the method does fine. And so as a final remark, I would say that yeah, these things are valuable tools for Quasinormal modes, and in general, any differential problem that is particularly challenging or for which you don't have a code that's already implemented or a very straightforward way. Okay, so I end up in some acknowledgements in our current projects in Aveiro. Thanks a lot for your attention.
Thank you. So, any questions?
we already talked about it, so I guess I can check my email to what that was, but I don't remember. There's a spectral bias, right? On neural network, they have a hard time finding solutions with high frequencies. So I
Spectral,
guess. So they have a hard time finding, they tend to find first the low frequency.
the mode. Yeah.
And so that, I guess, would also translate to the modes, they tend to find the low
So-
frequency mode.
So yeah,
So
I mean the
what's your
overtones.
strategy to find the higher frequency ones?
Well, there's no good strategy with any method to find the overtones. I mean, the only, particularly when you have these numerical backgrounds, it's really hard. I mean, you can find a few of them, but it's usually quite hard to find overtones. I mean, even with spectral methods, you get 3, 4, maybe at most. So for instance, for Kerr partial, you can Lever's method, the continuous fraction method, is able to find, I don't know, over 100 volts, okay? But that's something that's mostly for that method, I would say. In our case, what we can do is start with a different guess or impose some constraints on the network. So for instance, you can impose that, okay, I want to have a node here, I want the function to cross here somewhere. Or I start with an initial guess that I know it's close to the second overtone. And then the method can converge there. So if I start in the Bayesian abstraction of another mode, it might go there. But yeah, it's not an easy task. I mean, we found a few of them, but especially in Kerr.
So in care, you can reproduce them?
In Kerr, we found some of them, not many.
I'm guessing that you're the initial guess to your function.
Yeah. So what we do here, since we have the solution like structured in a 1 parameter family, like in a branch, we start with the one closest to the function.
Okay.
And then I take a value that's close, more or less close to the partial value, but it doesn't have to be. You can just put 5 or something like that. And then from there, it's kind of easy to go the first mode, structure light mode, and then I use that for the next. So I just keep using that, and this way I can go to very, exotic solutions without looking at that.
If you enjoyed the video, like and subscribe.